In this video, we're going to find out some more information about these things. So remember back into the basics of waves video, I mentioned a thing called phase. So this video here is going to use that quite a bit, so make sure you're on top of that. If not, we'll have a brief introduction into phase right now. So, if I have two waves, both in the same medium, so the same substance they're going into, so it could be air, it could be water, and they're also the same type of waves, so they're both electromagnetic waves of the same frequency. Alright, these waves are in phase if my first wave is being produced by starting with a crest, and my second wave is produced by a crest. So I have two waves, both of which are starting with a crest. And then they continue on with the same frequency and the same speed from there on. They're both basically exactly the same wave. They're what we call in phase. If our waves are not in phase, then they're not going to match up at all. They're a different frequency, they're different, they could be different speeds, it could be something like that. But what happens if this top wave here starts off with a crest, but this bottom wave starts off with a trough? Now, they're still the same frequency, travelling at the same speed, they're the same type of waves, but they're what we call not 180 degrees out of phase. So if we just lined them up 180 degrees, so this one here then started with a trough and this one here started with a trough, they'd be in phase. But we can see that this top one and this bottom one are out of phase by exactly half a circle, or 180 degrees. So they're half a wavelength out of phase. So we can have these slight differences in the phase, so out of phase by say 90 degrees or quarter of a wavelength or something like that, but we have to specify this. So two waves are in phase if they have the same frequency, they're travelling at the same speed, they're the same type of wave, and they have the same parts starting with or travelling with. So now we've had a recap on phase, we're going to move on to monochromatic light. So what do I mean by monochromatic light? So, monochromatic light is where we have a light source which is producing light of one frequency only. So, it's not necessarily just one colour, although we'll see it as one colour, because some light sources of one colour aren't necessarily just one colour. So if I look at an old-fashioned incandescent light globe, which we're going to get into a little bit more later on when we get to incandescence, but they look somewhat yellow. So we would say, oh yeah, it's yellow light coming out of it. That's not right. It is a range of frequencies, but there is just an abundance of frequencies around this yellow wavelength. So we see this yellow. So monochromatic light is where we have a light source producing a electromagnetic wave in the visible light range where it has one frequency. Coherent light sources, or coherent wave sources, are where we have two or more waves which are in phase with each other or in a phase relationship, and they have the same frequency. So we have coherent sources of waves if they have a phase relationship at the same frequency and they're travelling at the same speed. So ultimately they're the same wave but slightly different, or they could be slightly out of phase. But as long as we know the relationship and they maintain this relationship throughout their movement. So that's a coherent light source or a coherent wave source. In this video so far we have covered phase relationships, we've covered monochromatic light and coherent wave sources. So now we're going to be moving on to incandescent light sources. So incandescent light sources are where we are giving a solid or a liquid energy until the point where it starts to light up. So if we look at an example I've got here, I've got an oxyacetylene gas torch and I'm going to heat up this piece of metal. When I heat up a piece of metal, what do we see? So when you give the metal energy through the source of heat, it begins to light up. It produces a very bright sort of orangey reddy glow, and you can actually increase this until it gets to a white, but we're going to keep it at a sort of orangey colour. So we can see that I've given this piece of metal heat and it's produced light. This is exactly what an incandescent source is. So it's a solid or a liquid that when you heat it up or give it energy, it begins to show light. Another example of this is the old-fashioned light globes that you may or may not have around your house. So light from an incandescent source is neither coherent or monochromatic. Why is this? So if we look onto the particle level of the substances, so the tungsten filament in an incandescent light globe, or the iron that my steel is made out of. So we have molecules inside this. So these molecules, when they're given heat, vibrate. They're vibrating already when they're in just normal room temperature, but when we give them heat, they vibrate even more. So this vibration produces a range of frequencies. So these range of frequencies produce our light that we see, but we get a range. We don't just get one single frequency being produced, because the molecules could be moving slightly different speeds to one another, producing these range of frequencies. So when you heat up an incandescent source, so it's a solid or a liquid, when you heat it up, it produces light. It produces light which has a range of frequencies. So incandescent sources are not coherent because, remember, coherent sources are ones that are in phase or have a phase relationship with each other and have the same frequency. And they're not monochromatic, because monochromatic light are only sources of the same frequency. So incandescent light sources are not monochromatic or coherent. The key points from this video today. A phase relationship in waves are where we have waves which are the same frequency, travelling at the same speed, and they have some form of relationship between where their crests and troughs are, or what wavelength they are, and things like that. So if I had two sources of waves, and one began with a crest, one began with a trough, they're what we call half a wavelength out of phase, or 180 degrees out of phase. As long as they have the same frequency, they travel at the same speed, and they continue to move at this same motion, and they're in the same medium. So wave sources that are in phase have the same frequency, the same speed, they're in the same medium, they're the same type of wave, and they also start at the same point. So if I have a trough here on the bottom one, I have a trough on the top one, or so on and so forth. So monochromatic light sources are where we have electromagnetic waves being produced by a source of the exact same frequency. So all of the source of light that you see have only one frequency from this substance. A coherent wave source are where we have waves, so two or more, which have a phase relationship. They're not necessarily in phase, they can be, say, 90 degrees, 180 degrees, so on and so forth, as long as they maintain the same phase relationship and they have the same frequency. They travel at the same speed, same wave, same medium. An incandescent light source is neither coherent or monochromatic. This is because of the molecules that make up an incandescent light source vibrate independently of each other and produce wavelengths which are going to have slight differences between each other. So we get a range of frequencies being produced from heating up an incandescent source. So that is it on phases, monochromatic light, coherent and incandescent light sources.